Length contraction can be difficult to understand. Let's look at a visual example of what's really going on with the help of two subjects. We'll call them Observer 1 and Observer 2. Let's start with the railway car example. For this example, Observer 2 will be the one in motion. We've replaced the railway car with a real car, but the process remains the same. Observer 1 will be our stationary observer on the ground. We'll mark 2 points around 100 meters apart. Observer 1 measures the distance between these points as the full 100 meters. This is known as proper length. It is measured by an observer that is stationary relative to the points. As Observer 2 passes the points, they will measure the time it takes with a stopwatch. This measurement, as seen by the observer moving relative to the points, is called proper time. It is important to note this measurement will only work if the subject moves at a constant speed. Observer 1, our stationary subject, also measures the time. From their perspective, we refer to this as the measured time. The value for measured time can be calculated by this formula. When we multiply both sides by velocity, we get this. For Observer 1, the time Observer 2 travels multiplied by their speed will just be the proper length. Similarly, for Observer 2, their speed multiplied by the time measured in their reference frame gives us a new length, known as relativistic length. Plugging these new values back into the formula gives us the formula to calculate proper length based on relativistic length and the Lorentz factor, or vice versa. Since the values for proper time and measured time are different, the length measurements follow the same pattern. LM, or relativistic length, will always be shorter than proper length. This effect is known as length contraction, the spatial counterpart to time dilation. If we visualize this, the distance between the 2 points will become contracted for our moving subject, Observer 2. They will see the distance between the points shorter than it actually is. Now let's look at a different example, the meter stick example. Once again, we'll be replacing the meter stick with something else. This time we will use a jet. Observer 2 and the jet will be in motion, while Observer 1 remains on the ground at rest. Since Observer 2 is moving with the jet, they are considered stationary relative to the jet. From our previous knowledge, we know that their measurement of the jet's length will be the proper length. In this case, we will make it 20 meters. Observer 1 will measure the jet's length as it passes by. This will be the relativistic length and will be shorter than Observer 2's proper length measurement. Another way to look at this is as Observer 1 now being the one in motion. Even though they are at rest relative to the ground, when we look relative to the length of the jet, which is moving, Observer 1 is technically moving in the opposite direction. For this reason, their measurement of the jet's length will be the relativistic length and not proper length. Observer 2 is at rest relative to the stick, so just like before, they will measure the full length of the jet, the proper length. In this example, Observer 1 uses proper time to measure relativistic length, which will be contracted, and Observer 2 measures proper length, but must use time dilation for the measured time observed. To summarize everything, an observer that is moving relative to an object or distance between 2 points will see the distance become contracted under length contraction. They will measure length as relativistic length and time as proper time. An observer that is stationary relative to the object or points will see the proper length and measured time instead, based on the moving observer's speed. Hopefully, this video has cleared up any confusion you may have had on the topic of length contraction. Thank you.